Welcome to the lecture on types of weld cracks. So, we have talked about the cracks and what are the different types, and we will talk about in detail the cracks and especially about the hot and cold cracks in this lecture. So, coming to the hot cracks, if you recall, we talked about these hot cracks in that you have hot crack that may occur in the weld bead zone, or so that where weld metal zone where it is the solidification cracking, or you may have the lamellar cracking. Now, if you talk about the factors which will be promoting these hot cracks, so there are different factors which promote these hot cracks. So, the first point is the solidification structure. So, the solidification structure means, as we know, that in the case of weld solidification, you have the type of solidification which is observed is the epitaxial type of solidification. Now, in that case there is also the as the temperature is higher, so you will have the coarseness of the structure. So, you will have the epitaxial solidification that causes the coarseness of the weld deposit, causes coarseness of weld deposit. So what is happening, that too also that is inherited from the grain growth zone of the HAZ. So, that basically, now what is happening, that you will have long sided columnar grains. So, and that will so in high speed welds, basically that will be tending to be weaker under the stress than that another kind of grain, that is your equiax type of grains. So, which is normally observed in the case of low speed welds. So, in those cases, so that is what the type of solidification structure which you obtain, that also affects the cracking tendency, because that will promote in the case of high speed welding. So, you will have these columnar grains which occur. So, so in the case of columnar grains, you have the higher segregation tendency, and that leads to the formation of the cracks. Now, as we know that you have the dendritic type of structure. So, you will have dendritic growth is there in the case of weld metals, and we have already studied about the phenomena such as constitutional supercooling, which is observed when we talk about the alloys. So, in the case of solidification of alloys, you have the chances of the formation of the dendritic structures because of the constitutional supercooling, and in that case you have the chances of higher segregation. So, as we know, if you recall the phenomena of segregation. So, the second point which is important is the segregation. So, segregation is another point which is very important factor for the hot cracking to occur. Now, this is we have already studied about the parameter, that is your partitioning coefficient, which is there when we talked about the binary alloys phase diagrams. So, in that we had studied about the partitioning coefficient. So, normally segregation is unavoidable in case of alloys, because you have the partitioning of elements during the initial stages of solidifications, and we also define these partitioning coefficient. So, partitioning coefficient is defined as the XS upon XL. So, so as we see that when we talk about, if you recall that when you had these phase diagrams, so you have if you come to any temperature. So, now here you will have this is your if you come to this is your XS and this is your, and if you come here, so at any particular temperature you have this as XL. So, you will have XS upon XL, and it will be either less than 1 or it will be more than 1, depending upon how this binary phase diagram looks like. It may go like the slope may be less than 1 or more than 1, something like. So, positive or negative, in fact, not more or less than 1. So, basically this leads to, so because of these partitioning coefficient values, so you will have the alloying constituent which is there in the weld deposit. So, so you may have the lower value of K, or you may have the higher value of K, and most likely these elements which normally are segregating, they are the like sulfur, oxygen, boron, phosphorus, carbon, titanium, all these elements, nitrogen and hydrogen. So, they are normally trying to segregate, and you have the segregation coefficient, that is partitioning coefficient values are there. So, that can be found out from the tables in the standard books. So, so that way so you have when, so normally the rule is that if you have the slow solidifying weld, so and so with the coarse microstructure, so they will be promoting center line segregation normally. So, if so the condition is that if you have slow solidifying weld and also with coarse microstructure, so in those cases normally this is the case in the case of welding process such as electroslag welding. So, in those cases you will have more segregation likely to occur. So, that is there in the case of electroslag welding processes or so. Then the another factor which is important is the residual stresses. So, if you talk about the formation of the residual stresses. So, as we have already studied that the stress value should not reach to a higher limit. Otherwise, once that crosses that limit, then that may lead to the cracking. So, that way you will you should have the control of the residual stresses. Then you have the material thickness. So, as far as the material thickness is concerned, so thicker will be the material. So, faster will be the cooling after the welding, because in most of the cases in welding, when you are surrounded with the metal with large, which has normally the higher value of thermal conductivity. So, if your cooling rate is fast, in that case you have the probability of formation of harder constituents, and once you have the more probability of the formation of higher constituents, in those cases you will have the more chance of formation of cracks also in the in that weld metal. Then the next factor is the restraint. We have already studied about the restraint which is there in the case of welding. So, many a times we are using the jigging or use of jigs or clamping we do. So, we are providing these restraint, and so if the hot strength of the weld metal is exceeded, then that if so the stress which is generated, if that exceeds the hot strength of that weld metal, in those cases there is likelihood of the formation of cracks. So so you have to minimize these restraint on the joints. So that is that should be the practice, that your joint restraint should be minimum, and for that you must have the provision for the some space between two members, so that they can have the movement during the cooling. So if you provide those spaces for their movement between the cooling, then these effect because of these restraint that can be minimized. And many a times we we try to do do certain measures to minimize these joint restraint. Then the next factor which is further important will be the weld bead shape. So you may have the convex type of shape, or you may have the concave type of weld bead shape. So in that normally when you have the concave weld bead shape, so if you have a concave fillet, now that appear to be larger. So suppose if you talk about, so you may have such kind of shape, or and that moves, or you may have this kind of shape, and that moves. So that way so concave shaped fillet will be there, and that will be larger than these convex weld, and then you will have but these concave type of fillet, they will have the lesser penetration into the welded plates, and so that they will have the smaller throat than the convex type of bead. So the convex bead normally which you get, they appear to be stronger. So although they appear to be smaller, but they normally are smaller, because here the penetration is smaller, so it is shallow. So that gives you more strong. But however, in many cases these concave type of the bead shape is preferred by the designers, because there will be smoother stress flow to resist the load on the joint. So that is the trait of this concave type of weld bead shape. But when when you have these concave bead, then when it cools and then shrinks, at that time the outer surface will be under tension, and then there may be cracks. So on the contrary, when you talk about the convex bead, so they have normally you have very reduced shrinkage stresses in surface area, and the possibility of crack during the cooling is normally smaller. So that way this is the these are the traits about these concave or the convex type of bead shape, and the shape plays one important role towards the development of cracks. Then another factor which is also important is the width to depth ratio. So normally the width to depth ratio should not be very high, but it should not be less than 2/3 also. So W by D, that value it should not be less than 2/3. So these are the well designed principles which are followed, and if your depth basically is very large than the weld width, So, so what happens that may freeze. So, if the depth is very large, then the width. So, so before the center freezes, the surface may freeze. So, that may be the consequence of the that factor, and when this will be happening, in that case the shrinkage force will act on the frozen center. So, so that will cause a crack. So, that happens normally. So, that should be avoided. You must have the proper width to depth ratio. Apart from that, you may have other factors like you have the material composition. So, what is the composition of the material, and some of the materials amounts should be limited, and normally we try to avoid the higher percentages of some elements like carbon or nickel, because the presence of these elements increase the hardenability of the steel, and whenever the hardenability will be increased, then their susceptibility towards the crack formation will be higher. So, we should try to have minimum amount of minimum value of these elements in the material, so that the crack formation tendency is smaller. Then comes the effect of the welding procedure. So, if you talk about the welding procedure, so what we see normally is that if you use the high welding speed, and if you are using the long arc length, so high welding speed and long arc length, so they promote the the development of arc, these cracks. So, promote crack formation. So, that is there in the case of that is the effect of these welding procedure. And towards the end, you have also many a times we have studied that if there is a poor fit up or inadequate tacks, so that also leads into the formation of cracks. So, poor fit up means you have the reduced throat thickness many a times. So that leads to the poor penetration, and so that will be and proper and there is poor fit up. So that leads to the formation of cracks. Similarly, if you are providing the inadequate tacks also, so that also leads to the cracks. So, these are the factors which are responsible for the formation of hot cracks, that is especially the solidification cracks which are occurring in the weld pool. Now, coming to the different other type of crack, that is your liquefaction cracking. So, liquefaction cracking, as we know, this is also known as the burning. So, that is occurring normally in HAZ. So, in HAZ zone, and normally it will be occurring with the processes such as the electroslag or SAW process. So, they are high heat input processes, and also we had studied that in these cases you have high ratio of sulfur and phosphorus with low manganese content. So, this is typically for steels. When this is the case, in that case your liquefaction cracking becomes predominant. So, in the liquefaction cracking, basically what is happening, that when you have the hot rolling of the plate, when you are manufacturing. So, in that case you have the sulfur and phosphorus that will be collecting around the grain boundaries, and they are normally in the form of low temperature eutectics. So, you have the iron phosphide, or you have other typical compounds which are basically the low temperature eutectics, and the prolonged heat which is passing. So, that heat, basically what happens, that when it passes through that, and since it is a low temperature eutectics, so when it passes through that region during the welding process, then that melts that region, and then that eutectic phase will become basically the semi molten or in the molten state, and then once they cool, then they will be forming the brittle films around the grains in the HAZ. So, normally this is the main reason of the liquefaction cracking, because the sulfur and phosphorus. So, that is why we try to minimize these components, because they will be even if in that HAZ zone, which is not going to that temperature where there is melting, but then you get these low temperature eutectics which is there inside that region, and along the grain boundaries they will be. So, you will have the brittle film formation around that grains. Now, because of the stresses which are induced in this contracting material, now that results into the micro cracking of these zones, and so that will be reducing the strength and ductility of the material. So, so that the cracks which are formed, these cracks are normally known as the liquefaction cracking. So, basically as we know that the liquefaction cracking, that is dependent upon the amount of impurities which is there in that base metal, and depending upon the volume percent and amount of the and as well as the density of also the inclusions. It will be also depending upon the degree of restraint. So, so the liquefaction cracking, so that will be is dependent upon amount and type of impurities in the base metal, and volume percent and density of inclusions and degree of restraint. So, all these factors basically will be will be controlling these liquefaction cracking. So, and basically you will have the high energy welding processes, they increase the susceptibility to these problems. The dwell time in the high temperature zone, that also is very important. So, that is why these high energy welding process basically aggravate these liquefaction cracking during the welding. Now, this is about that liquefaction cracking. Now, another type of cracking which is more importantly to be studied is the cold cracking. So, as we had studied that the cold cracking is also known as the HIC or hydrogen induced cracking, and it is also known as the delayed cracking. So, it occurs late. So, it is known as the delayed cracking, and normally you will have the when you have the welding of high strength steels, then these cracks are developed, and the factors which are present simultaneously, which are responsible for these type of cold cracking, are the hydrogen in weld metal, then you have the high stresses, you have the susceptible microstructure, that is the formation of martensite, and also you have relatively low temperature, that is between 200 to minus 100 degree centigrade. So, normally what happens that you may have the there are many constraints like heat input constraint, or you have the other constraints that induces the high stresses. One is the presence of hydrogen, so that has to be minimized. Then you have high stresses, especially when your martensite is formed, so that results into high stresses. So, so under that case you will have more susceptibility towards the formation of these cold cracking. And if the martensite this finished temperature, that is your or start temperature, martensite formation temperature, that is MS, if relatively it is low, then the HIC will be relatively occurring at the lower temperatures, and that is why this name is the cold cracking. Now, the main source of this cold cracking is normally the presence of hydrogen in that weld metal, and you will have the presence of water vapor which is in the welding arc. So, basically hydrogen which is there in the atomic form, now that can easily penetrate into the steel and that can cause cracking. So, the water vapor which is there, that will be broken and you will have the hydrogen in the atomic form, and this can penetrate and that can provide the cracks. You have the blisters formation, and also that will be resulting into the loss of ductility. So, so what is important is that this one of the trait which is there of these type of cracks is that it can even go into a very high hard areas also. So, like it can be appear in the area of heat affected zones, and also it can appear in the area of localized hard spots. So, that way it can be found in those areas too. Also if you can understand by the presence of these type of cracks. So, normally the components which will be failing by the cold cracks. So, you will have at some times you will see that they have the fish eyed type of phenomena. So, you have the circular areas of quasi cleavage fracture centered on a large inclusion. So, that is you will have the clusters of smaller inclusions will be there, like you have silicates or Al2O3 particles. So, that is normally what you see in these cases of cold cracking. Apart from these hydrogen which is or water vapor which is there, you can have the presence of hydrogen from other sources also, like the hydrogen can come from the corrosion reactions, it can come from the chemical processing reactions. Then you have many a times because of the purposeful additions also. So, so from all these sources the hydrogen may go. We use the many times the coatings also in the shielded metal arc welding, you use the coatings. So, therefrom also there may be susceptibility of there may be absorption of hydrogen, so that may go into the weld. So many a times we do something, so there is some moisture if it is there. So we try to avoid these moistures by preheating those electrodes also. So that is also a common way to avoid the cold cracking phenomena. So if you try to sum it up, you can promote these cold cracking in weldments by the formation of these by the presence of hydrogen in the weld metal zone. You may have the joint restraint and high thermal conductivity that may also result into the high stresses. You may have the presence of impurities, you have the susceptible microstructures, then you have lower current density because of that low temperature is there, or insufficient cross sectional area is there. So that way these are the reasons because of which these cold cracking occurs. We will talk about the specific type of cracks in our subsequent lectures. Thank you very much.